3 minutes ago, Google's quantum computing division confirmed something cybersecurity experts have quietly feared for over a decade. The encryption protecting your bank account, your passwords, and every Bitcoin wallet on Earth just moved dramatically closer to being broken. And the people who built the machine capable of doing it are the ones telling you. The announcement came from Google Quantum AI, the same division that built Sycamore and now the far more advanced Willow processor. For years, quantum computing has been treated almost like a distant curiosity, a science experiment decades away from touching everyday life. That framing just changed. In a paper published in Nature on July 8th, Google researchers revealed a breakthrough that solves one of the field's most stubborn problems, keeping a quantum computer stable and accurate while it is actually running. To understand why this matters, you need to understand what has been holding quantum computers back all this time. Qubits, the basic units of quantum information, are incredibly fragile. Unlike the simple ones and zeros inside your laptop, qubits exist in delicate superposition states that can be knocked out of alignment by heat, vibration, or even stray electromagnetic noise. Historically, engineers had to pause the entire computation periodically just to recalibrate the hardware, an interruption that ate away at the very uptime quantum machines desperately need to outperform classical computers. Google's new system removes that limitation entirely. Using a reinforcement learning agent, an AI system that learns and adapts in real time, the Willow processor can now continuously tune its own control parameters while the calculation is still running, without ever stopping to recalibrate manually. According to the published results, this single change reduced logical error rates by roughly 20%, beyond what conventional calibration could achieve, and made the system 3.5 times more stable when researchers deliberately introduced hardware drift to test it. Google's new system removes that limitation entirely. Using a reinforcement learning agent, an AI system that learns and adapts in real time, the Willow processor can now continuously tune its own control parameters while the calculation is still running, without ever stopping to recalibrate manually. According to the published results, this single change reduced logical error rates by roughly 20% beyond what conventional calibration could achieve, and made the system 3.5 times more stable when researchers deliberately introduced hardware drift to test it. The technical details matter here, even in simplified form, because they explain why researchers are treating this as more than routine progress. Willow uses what are known as surface codes, specifically configurations described as distance 5 and distance 7, along with a distance 5 color code, all methods of spreading a single unit of quantum information across many physical qubits so that errors in any one of them can be detected and corrected without destroying the underlying data. The higher the distance number, the more physical qubits are dedicated to protecting a single logical qubit. And historically, scaling those distances up has only made the calibration problem worse, not better. Google's reinforcement learning layer appears to solve that scaling problem directly, allowing larger, more error-resistant configurations to actually become more stable rather than less, which is the opposite of what engineers have struggled against for years. If you're new here, this is exactly the kind of story we break down every week before the mainstream outlets even understand what it means. So go ahead and subscribe now, because what this breakthrough enables is where things get genuinely uncomfortable. For most of quantum computing's history, encryption has been safe for one simple reason: no machine could run long enough, or reliably enough, to crack the mathematics protecting modern digital security. Elliptics, curve cryptography, and RSA encryption, the systems guarding everything from online banking to government communications to the private keys behind every cryptocurrency wallet, rely on math problems that are essentially impossible for classical computers to solve in any reasonable amount of time. A sufficiently powerful, sufficiently stable quantum computer changes that equation completely, and stability was always the missing piece. That is precisely what Google just solved. A quantum processor that can self-correct its own errors continuously for extended periods without human intervention is no longer a laboratory curiosity that works for a few seconds under perfect conditions. It is a system that edges meaningfully closer to sustained large-scale computation, the exact kind of computation needed to run the algorithms capable of breaking modern encryption. This is not a theoretical leap being made by outside commentators either. Back in March, Google Quantum AI released its own white paper suggesting that improved methods for compiling quantum algorithms could reduce the scale of hardware needed to compromise elliptic curve cryptography, the backbone of blockchain security. In their own words, the threshold for what researchers call a cryptographically relevant quantum computer, a machine actually capable of breaking real-world encryption, may be closer than earlier estimates indicated. That statement from Google itself was already alarming enough on its own months ago. Now, with a hardware stability breakthrough sitting on top of it, the timeline that once felt comfortably distant suddenly feels a great deal shorter. Security researchers have warned about this exact moment for years under a term you may have already heard: harvest now, decrypt later. The idea is simple and deeply unsettling. Encrypted data being intercepted and stored today, financial records, private communications, government files, cannot be read yet, because no machine currently exists that can break the encryption protecting it. But intelligence agencies and cyber criminals alike have reportedly been quietly stockpiling encrypted data for years, betting that a quantum computer capable of unlocking it is only a matter of time. Every breakthrough, like Google's, brings that stockpiled data one step closer to becoming readable. Security researchers have warned about this exact moment for years, under a term you may have already heard: harvest now, decrypt later. The idea is simple and deeply unsettling. Encrypted data being intercepted and stored today, financial records, private communications, government files, cannot be read yet because no machine currently exists that can break the encryption protecting it. But intelligence agencies and cyber criminals alike have reportedly been quietly stockpiling encrypted data for years, betting that a quantum computer capable of unlocking it is only a matter of time. Every breakthrough, like Google's, brings that stockpiled data one step closer to becoming readable. Consider what that actually means in practice. A piece of encrypted communication, intercepted 5 years ago and stored on some server, seemingly worthless at the time because it could never be decoded, does not become safer with age. It sits there, waiting, and every year that quantum computing advances, the value of already stolen encrypted data effectively increases rather than decreases, because the odds of it eventually being unlocked keep climbing. That is precisely the calculation. Intelligence agencies and cyber criminal groups are reportedly making right now, and Google's announcement this month just shortened the wait considerably from where it stood at the start of the year. The cryptocurrency world has particular reason to be nervous about this news. Bitcoin and most major cryptocurrencies rely on exactly the kind of elliptic curve cryptography Google's own researchers flagged as increasingly vulnerable. Wallets that have never moved their coins, some holding keys generated over a decade ago using older, less robust standards, are considered especially exposed because their public keys have already been exposed on the blockchain for years, sitting and waiting for the day a machine becomes powerful enough to work backward from public key to private key. Estimates of exactly how many coins fall into that vulnerable category vary, but the number is large enough that entire teams inside major exchanges are reportedly reassessing their quantum readiness timelines this month alone. To be clear, Google's Willow processor has not broken encryption. Nobody at Google Quantum AI is claiming your bank account is unsafe tonight, and the reinforcement learning breakthrough published this month is fundamentally a stability improvement, not a working attack on RSA or elliptic curve systems. Responsible reporting on this story has to include that distinction clearly. What changed is not that encryption fell today. What changed is that one of the biggest remaining obstacles standing between today's quantum computers and a machine capable of eventually running that attack just got meaningfully smaller, and it got smaller faster than almost anyone in the field expected. Government agencies have not been sitting idle while this unfolds. The National Institute of Standards and Technology has spent years developing post-quantum cryptography standards, new encryption methods specifically designed to resist attacks from quantum computers, and major tech companies have already begun migrating some systems toward these newer standards. The uncomfortable question this breakthrough raises is whether that migration is happening fast enough. Post-quantum cryptography takes years to fully roll out across the global financial system, government infrastructure, and everyday consumer technology. If the timeline for a cryptographically relevant quantum computer just compressed, the timeline for finishing that migration needs to compress right along with it, and right now, there's no guarantee that it will. The scale of that migration problem is easy to underestimate. Replacing an encryption standard is not like pushing a simple software update to a single app. It means rewriting security protocols baked into decades old. Banking infrastructure, government communication networks, medical record systems, and hardware that was never designed to be easily replaced. Some of these systems date back to the 1990s, running on hardware that predates modern cybersecurity practices entirely, and swapping their encryption standard can take years of careful, coordinated engineering work across multiple industries at once. Security teams openly acknowledge that some organizations will not finish this transition before a cryptographically relevant quantum computer arrives, which is precisely why the harvest, now decrypt later strategy remains such a serious concern. This urgency is not confined to research papers and press releases either. It is already showing up in government funding decisions. Just this month, the Block Quantum Tech Hub, a multi-state consortium spanning Illinois, Indiana, and Wisconsin, secured $55 million in federal and matching grants specifically to build out a domestic quantum supply chain, reducing reliance on foreign-made hardware components. The funding is being split across manufacturing transition services, industrial scale supply chain integration, security and capital mobilization, and physical infrastructure build-out. Money like that does not get allocated at that speed for a technology anyone still considers purely theoretical. Governments spend when they believe a timeline has become real, and this kind of rapid, targeted investment is one of the clearest signals yet that quantum computing is no longer being treated as a distant, someday problem inside the halls of federal funding committees. There's also a broader pattern worth noticing here, one that goes beyond any single headline. Google's Willow chip has already produced two of the field's most talked about milestones. The original 2019 result that first demonstrated a quantum computer outperforming classical machines on a narrow task, and last year's error correction breakthrough that showed, for the first time, that adding more physical qubits could actually reduce errors instead of compounding them. This month's reinforcement learning advance is the third major leap from the same hardware lineage in under a decade, and each one has arrived faster than outside experts predicted the one before it. That accelerating pattern is exactly what has cybersecurity researchers uneasy, because a field that keeps beating its own timelines is a field where comfortable distant deadlines have a habit of quietly becoming urgent ones. NVIDIA researchers and academic partners published their own paper late last year making a related point, that artificial intelligence and quantum computing are converging in ways that reinforce each other, with classical AI systems increasingly handling the optimization and error correction work that makes quantum hardware usable at scale. Google's reinforcement learning breakthrough is a direct, real-world example of exactly that convergence happening. It is not simply a quantum computer getting better on its own. It is a quantum computer getting better because an AI system is now watching it, learning from it, and correcting it in real time faster than any human engineer could manage. That combination, quantum hardware plus adaptive AI control, is precisely the kind of pairing researchers have warned could compress decade-long timelines into a handful of years. None of this means encryption collapses tomorrow, and it's important to say that plainly, rather than exaggerate a genuinely significant story into something it isn't. But it does mean the conversation has shifted. A year ago, a cryptographically relevant quantum computer was widely described as a problem for the next decade. After this month's announcement, fewer researchers in the field are willing to say that with the same confidence, and some are now openly discussing timelines measured in years rather than decades, a shift in tone that matters just as much as any single technical result. Google Quantum AI has stated it will continue publishing its findings openly, framing this as responsible disclosure meant to give governments, banks, and the crypto industry time to prepare rather than be caught off guard. Whether that window of preparation is actually being used effectively is a separate question entirely, one that security experts and blockchain developers are now asking with noticeably more urgency than they were even a few months ago. What we do know for certain is this. The single biggest technical obstacle keeping quantum computers unstable long enough to threaten modern encryption just narrowed, confirmed in Google's own published research, verified in a peer-reviewed journal, and openly discussed by the very engineers building the hardware. That confirmation is the part that separates this story from years of speculative headlines about quantum computers someday breaking the internet. This time, the evidence is sitting in a peer-reviewed paper with Google's own name attached to it, not in a rumor or a leaked slide deck. And whether you keep your savings in a bank, a blockchain wallet, or anywhere in between, the math protecting it just got a little less certain than it was 3 minutes. Hey go, hit subscribe and turn on notifications so you don't miss what comes out of this story next, because if this pace continues, the next update might not be measured in years anymore. It might be measured in months, and given how quickly this field has already surprised its own engineers twice in the last 2 years alone, months might turn out to be a generous estimate.